Hi, I'm Morten. Today I'm standing next to Aalborg University's testing basin, where we have just completed a comprehensive series of experiments with the floating power plant WindFlex platform. In previously shared videos, I've explained the scaling of the device, the construction of this model, and how we have used this instrumented setup to complete more than 500 successful tests. In this video, I'll walk you through how this data is being applied to enhance our simulation models. Specifically, I'll demonstrate how we calibrate a calculation model based on the equation of motion, translating experimental results into simulations that will further improve the efficiency and reliability of our designs. Let's take a look. The presentation is split into three parts. First, I'll briefly introduce the experimental model. If you'd like to know details about the model, I would recommend that you watch some of the other accompanying videos from the campaign. Then I'll describe the math behind the simulation tool, which is based on the equation of motion. As the last and main part of the presentation, I'll demonstrate examples of different types of tests which were performed to validate the simulations. To validate and calibrate the numerical tools used for designing the platform, we constructed a scale 1 to 50 model to be tested in the wave basin. We simplified the model by removing the moorings and the wind turbine. We installed a force sensor on top of the model which holds the model, and we installed an actuator that allows motions of the model. The motion of the structure is usually calculated based on a mathematical equation called the equation of motion using inputs from linear potential wave theory. Let's look into that. Let's consider heave motion of the platform and vertical forces. I put on the forces acting on the platform. The pressure from the water on the hull is giving a hydrodynamic force. The mass of the device is giving a gravity force, and the restriction from above by the actuator are also applying a force. The forces can be put up in a force balance using Newton's second law. Force is equal to mass times acceleration. Using the formulation from linear potential flow theory, the forces are split up in contributions from wave excitation, wave radiation, and hydrostatics. But this formulation is not completely correct. So when we do simulations, we get a slightly different force compared to what we measure with the actuator. So we introduce a correction to account for nonlinear and viscous effects. Let's introduce that into the equations. So we simply add this correction to the equation of motion, and then when we solve the equation, the special effects are accounted for in a simple way. In this way, we calibrate the equation to give the correct results. Now we have the forces on the platform. What is important to understand here is that the contributions to the force from the water is split up in different contributions, and then these contributions are simply just added to form the total hydrodynamic force. In the following, I'll demonstrate how the small-scale physical setup with floating power plant is used together with this equation. We start out simple with simply moving the model by fast oscillations in air. In this case, we'll have only gravity force, and the inertia force will be proportional to the mass. On the upper plot, we see a time series of measured vertical acceleration and the forces measured by the actuator during the same time period. In the lower figure, I've shown measured data as dots with acceleration along the x-axis and force along the y-axis. We can see that all measurement points are on a straight line with the slope matching the mass of the platform. The next simple test is a hydrostatic test where the waterline relative to the model is changed slowly. The change is so slow that the accelerations are negligible and there are no radiated waves. This can be done by either moving the platform slowly or by draining and filling the basin slowly. In similar way as in the last slide, the data for the time series can be plotted. This time I've plotted the vertical position of the model relative to the water level on the x-axis, and in this way I get the hydrostatic curve. By comparing to calculations of linear and nonlinear hydrostatics, we can validate the calculations. I bring up this example with two ways of doing the same experiments. Sometimes this is possible. In this example, it was possible to validate the full hydrostatic curve using the change in water level, whereas the actuator was not strong enough to completely submerge the water. In the next type of test, we move the model with a constant speed in otherwise calm water. In the present example, we are moving the model upwards with a constant speed of 0.14 meters per second, which corresponds to 1 meter per second at full scale. The model scale test is very fast, so the video recordings from the lab is here played in slow motion by a factor 7 to visualize what it would look like in reality. In this case, we have merely a contribution from the hydrostatic apart from the correction. The data from the actuator are compensated for the hydrostatic force to get the correction force. The correction is considered as a drag force, and it is taken as a mean value of the measurements during a time window where the response is fairly steady. In the following type of tests, I put on incident waves, but I keep the platform fixed. In this case, we measure directly the wave excitation force on the platform. In the plots, I've shown the results of 3 simulation models, an advanced CFD model and 2 models based on potential theory. The simulations with the potential models are shown before the corrections are included. In the middle plot, I've shown results for the vertical force where all the models matched quite well without any corrections. But if we look into the moments seen in the lower plot, it is clear that the potential models could improve by including a correction. The procedure for the calibration is further extended to include more components of the equation of motion. Here I have shown 2 further examples, one for radiation on the left-hand side and a combined case on the right-hand side. Validation and calibration is in practice done for a variety of situations. So physical configurations with various motions in the different degrees of freedom and changes in the environment like wave direction, wave period, and wave height. In conclusion, we have seen that dedicated small-scale experiments with the floating power plant WindFlex platform were used to verify and calibrate the simulation tools. With the validated simulation models, we can refine and improve the floating power plant concept. The insights from this campaign will enable us to deliver more cost-effective and reliable platforms, making more competitive floating platforms in the rapidly evolving renewable energy market. As we move forward, these developments will be a critical part of shaping the future of offshore energy solutions. Thanks for watching.